Hi, my name is ThePrimeagen. I am a senior software engineer at Netflix, husband to a beautiful wife, and a father of 4. I created the last algorithms course you'll want because I wanted everyone to be excellent at algorithms. In this course, we go in depth on binary and M-way search trees along with graphs and some dynamic programming, and at the end, a special bonus algorithm. Having an advanced knowledge of algorithms is going to help you not just today, but for the rest of your software dev journey. I hope you go out and implement some amazing algorithms in your code base.
And we're going to insert these into the tree in particular orders, and we'll have to shape these trees. Okay, so we're going to start with case 1. If I started by inserting 42, then 69.
Nice.
There we go, thank you. And then 420. We would now hit a violation because at this point we are 0, 0, 0, 0, 1, 1, 0, 2, 2. We have now violated. Are we within our balance factor allowance? No. No, we are not. We must change it. So this is called, people call it an RR rotation. I don't really like this term because even though it is right-leaning, you do a left rotation. I don't know why it's called an RR rotation. I think this is the lean and we need to rotate out of it. I've never liked it, but it's very, very simple. All you do is drop down the 42. Break link, create link. Now, balance factor, 0, 0, 0, 0, 0, 0, 0, or 1, 1, 0. We've now created a balanced tree right here. So we can do the other side as well. So let's just pretend we inserted 420, then 69.
Nice.
All right, and then 42. All right, so now that we have that, we calculated 0, 0, 0, 1, 0, negative 1, 2, 0, negative 2. The balance, where are we going out of control? Well, you can tell how we're leaning, again, by the numbers sign. So this one is leaning left, or an LL, take the L rotation. All right, awesome. So now we need to do the same thing, but we need to do it to the right. We are gonna rotate to the right. Exact same thing. Drop this thing down. Awesome. So now we have 0, 0, 0, 0, 0, 0, 1, 1, 0. Now we have a proper, again, balanced binary tree. So it gets a little bit harder now when we go to the next 2 cases. So these are called double rotation cases, the double entendre of AVL trees. And so if we started with 69 first.
Nice.
Oh, yeah, there we go. And then, let's see, hold on. We don't want to start with 69 first. That would just be absolutely terrible. Never get anywhere with that. We're gonna actually start with 420 first. Then we're gonna do, sorry, I almost broke the thing. Then 42, then 69. Now this one, we got 0, 0, 0, 0, 1, 1, 0, or 2, 0, negative 2. Notice that we have a left-leaning, right-leaning situation. We have an LR rotation we need to do. Now this one's a touch more complicated. We start down here and we do a rotation this way. Then we finish it off with the classic double L rotation. We already know the double L rotation, so let's look at this little one. The little one, we're gonna move the 42 out here, and then we're gonna bring up the 69. So that means we look like this. So now we're in a 0, 0, 0, 1, 0, negative 1, 2, 0, negative 2. We've just created a rotation we already know how to handle. So then after we start here, we rotate here, we go up, we rotate here. So pretty straightforward rotations. And the exact same thing can hold true on the other side. We can do a 42, a 420, and a 69. Nice. And that would lead us to a 0, 0, 0, 1, 0, negative 1, 0, 2, 2. In other words, a right-left rotation is needed. So we'd have to do the small followed by the big, which means we're gonna have to move the 420 out here and bring up the 69. I'm actually at the edge of the screen right now. It's very exciting right now. So 69 would go right here, and there we go. So now we have 0, 0, 0, 0, 1, positive 1, 0, 2, positive 2, which means now we just drop down the 42, and now we have 0, 0, 0, bam, make that link happen, get rid of that thing, and now we have 1, 1, 0. We have balanced the tree. Now you're probably asking me, okay, this sounds really nice, but what happened if they all have children? Wouldn't that make the rotations really, really hard? Because it seems easy when you just do simple problems, but the moment you don't do simple problems, it gets excessively hard, right? Wrong. It's actually not all that hard. Man, why did you guys fall for the easiest trick in the book? Okay, we're going to erase all of this. Just get them all out of here. Everyone has the rotations locked in their brain? Yep, long as you follow the rule, the rotations are not hard. Just always think of the rule and what that means in placement. So let's look at this. I'm going to have A. I'm going to have B. I'm going to have C. And then I'm going to have AR, almost put L, BR, Brazilian mentioned, and then we're going to have CL, CR. So now let's do the rotation here, because at this point, we're going to just pretend it's 0, 0, 0, 1, 0, negative 1, and then it's going to be 2, 0, negative 2, okay? We're just going to pretend it's those numbers. It doesn't really matter. Inflate them to make it all work out. We need a left-left rotation here, okay? Boom, we're going to do this. So typically, you'd want to bring down A, but now we have all these kids, right? Like, look at poor Brazil. What are we going to do with this one? What do we do? Well, remember, what's the rule? What can we say about BR in relation to A?
It's less than.
It's less than. Beautiful. Ka-chow. Brazil moved. A here. What can we say about AR in relation to A?
It's greater than.
It's greater than. AR. What do we need to do with C? Nothing. It's great. It's beautiful. Therefore, it's 0, 0, 0, 0, or 1, 1, 0, 0, 0, 0. It's now balanced. It's fantastic. We just did it without having to do anything fantastic here. So you can see it's really not that hard long as you focus on the rule. This is the most important part. If it's not in your head, everything feels hard. Leaves. The simplest one we can think of is if we have k-min plus 1 keys. Right? We're somewhere between k-min plus 1 to k-max. If we just delete any of the keys, right? 10, 20, 30, let's just say we have, we're on an order 4 tree. That means our minimum is 1. If we were to delete any of these keys, well, that's actually really, really easy because you just delete the keys. There's no children. You just delete the key. Get out of here because we maintain all of our requirements. I'm going to bump this up to because it just feels nicer. I think it's easier to see. We're going to do an order 5 tree for the deletion part of things, which means I have to do a lot more writing, but I just think it's a little bit easier to kind of see how these things work out. All right, so we are still at our minimum, which is 2, so we're good. Now, let's just draw out some things here. I'm going to go 1, 2, 3, and let's get rid of this one. And that means we have to have, like, what, 5 up here? We have to have 15 right here, and let's have 25 right here. Yeah, that feels good. Oh, that feels just so good. We got to have this one. That means we have to have more keys. Let's not do that. Oh, we do want to do that. We do. Which means we need to come up with something right here, which will be, this one's not right. We need to do 12. We need to do, we'll do 16, 17, and then this last one will be 27, 28, perfect. And let's actually also add in an 18. All right, I'll rewrite it for you guys. I will rewrite it for you guys. 16, 17, 18, beautiful. All right, so now let's pretend we're deleting 28, or 28. We're deleting 12. All right, 12, we don't even, oh, we do have 28 on here. We're deleting 12. Well, we are at the key minimum, right? If our order is 5, our minimum is 2. Can we delete this key? I mean, the answer is yes overall, but can we just delete it by just removing it? No, not at all. So what we do, now remember, this is where we get to use our terms again. I erased it. Just a loser. Oh, man, imagine if I had it still up here. We need our in-order predecessor or our in-order successor to be able to do this. And it's kind of like that, but it's a little different, but it's the same thing. It's going to be effectively our in-order on our sibling on either side. It's the exact same thing. So either we're taking the largest of the small or the smallest of the large when it comes to leaves. We're going to say, hey, can we borrow that? So case 1, of course, we already talked about. Oh, 3 cases. Let's get rid of these cases. Let's move this to 4 cases. 4 cases. 1 k-min plus 1. We already did that one. That's easy peasy. The next one is kmin with left kmin plus 1. All right, so your left-hand side has enough keys to be able to spare, which means what we're going to do is we're going to take the 3 and we're going to move that 3 up to where the 5 is. We're going to take that 5 and move it to the front of the list down here. Because when you take from the minimum side, you move it to the front of the list. So now, can we delete the 12 easily? Yes, we've reduced case 2 to case 1, goodbye, you're dead. All right, so now we're going to do the exact same thing, except we're going to delete 10 now. All right, so this leads us to case 3, which is we are at a kmin with a right kmin plus 1. Fantastic. That means we need to take the smallest item from our larger sibling. You can't go 2 over. You have to go 1 over. Maybe there is a way you could find a way to like snake it through, but we're not going to do that because that would be just crazy talk. So what we're going to do is we're going to take 16, we're going to move it up to 15. Notice we're not violating any rules right now, right? We are maintaining all the rules of that. It's fantastic. So that means our 15 comes down and adds to the end of the list because again, it's on the larger side. The larger side goes to the end of the list. The smaller side goes to the beginning of the list. Choose your data structure wisely. Now we can delete 10 because now we've reduced case 3 to case 1. Beautiful. Delete, you're dead. All right, so now that we've done that, we want to delete yet again 15. What are we going to do here?
Do it twice?
Do it twice? Wrong! Great idea, wrong. Okay, I love the passion you have, but it's incorrect. I want you to kind of look at this list. Just imagine it for a second. What if the files were in the computer? All right, they're right there. It's already right in front of you right now. We could actually create a list called 1, 2, 3, 5, 15. We are going to merge it. This right now is in violation. It is kmax plus 1. This will always be kmax plus 1 because we did kmin twice plus 1 more. So that's always a violation rule. It's always kmax plus 1, which means now that our 3 came down and we're trying to delete 15, 15's gonna go away and we're gonna have a new tree. So let me just erase all of this. 3 goes out of here. And now we are sitting like that. It's now been deleted. All right, fantastic. We've done it. Now, there comes a point where a violation can then happen at your next level, which means that as you delete a leaf, you're then going to have to recursively walk back up the item until we find where a violation has happened. Now, again, you could do the exact same algorithm. You can look to the left, you can look to the right, or you merge upwards. You just keep on playing the same game over and over again as you fix the tree upwards. So if you don't know what a bloom filter is, it's pretty exciting. All right, it's a very fast way to tell if something is in a or not in a set. Meaning that, I know, that's kind of a weird way to do it because it's like, why not in? How it works effectively is that you have a series of hash functions. You have, say 3 hash functions. And you run through the hash functions marking into a set. We'll talk about that here in a second. And what a bloom filter can do is it can say, yes, something could be in this set. Maybe. We're not 100% sure. But it can say with 100% certainty if something's not in the set. And so Akamai uses this for what they call one-hit wonders. They use a more complicated version, but it's the same principle, which is, hey, this one website got loaded. Do we need to store this into CDN? Probably not right now. But what happens if we're going to see that site a bunch of times? Then we're going to want to see it. And we're going to want to put that into a special place where we can have it highly cached and it moves really, really quick. So it has the chance of false positives, but it has no chance of false negatives. If it's not in the bloom filter, it's not in the bloom filter at all. So let's go over what that means really, really quickly. It's pretty simple. Let's pretend we have 1 byte of data. Right? So this is 1 byte. All right. I have 8 bits, 1 byte. And we have a hash function that's pretty easy. If I provide a value, I'm gonna use the value itself. So that's one function, is just to return the value, modulo the length. We're gonna do another one where I square the value, modulo the length, and another one where I double the value and then modulo the length. So what is that going to look like? I wish I could do some bigger math, but I can't put like 69 in there because I don't know how to square 69 in my head and then modulo the length. Way too difficult, completely out of my powers. And I'm also going to just use 10 instead. Let's not, because 10 is just way easier to do modulo math on because you just use the last number and there you go. Fantastic. All right, so let's pretend we're going to store the value 10, right? So what is 10 modulo length? 0, right? So I just assume this is 0. This over here is 10. So therefore, I'm going to put a 1 right here. All right, then we're going to do the next function, which is say that's 100 modulo the length. That's a 1 again. All right, then we're going to double it, which is 20, which is 1 again. OK, we have a pretty crappy hashing algorithm, but let's keep on going. All right, let's do a 7. All right, 7 length. We're going to go over to 7, right? Oh, not a 7. I wrote a 7. 7 modulo length is 7 right here. 7 squared is 49. Modulo length is going to be 9, which is going to be this answer right here. Wait, hold on. That means 7's right here, huh? There we go. I'm really good at this. All right, and then the last one, double, which is 14, which means we're going to have the 14th one. 0, 1, 2, 3, 4. All right, there we go. So that is our Bloom filter for 7. So now let's say, does 8 exist within this set? Let's find out. So we'll do an 8. So 8 modulo the length is 8 right here. Does it exist in this set? No, it does not. We can just fast bail right out of it. We don't even have to think about it. It does not equal this set. All right, let's do, how about 9? We'll do a quick 9 check. All right, 9 modulo length. OK, maybe 9's in here. Let's do it again. What's 9 squared? 81 right here. It's not in here. So we know right away that 9 was not stored within this filter. So the thing about a Bloom filter is you don't remove values, because you can't remove values because there's some level of overlapping at any one point. And so that's kind of an important thing. So if we were to put 5 in here, we would go over here and we'd set 5 to 1. We would then square it again. It gets written right here. And then we double it, which is a 0, and then we'd go right here. And so you could imagine that if we try to remove 5, we would remove this as a 0 and this as a 0, which would also remove our value 10 out of here. So there you go. That's the basic principle of a Bloom filter. So here's where it falls apart. Let's say we do 20. All right, 20. What's the modulo of 20?
0.
0. OK, could be in here. What's the square of 20?
40.
400.
400.
0. Again, OK. Times it by 2?
40.
40. 0. OK, it could be in this set. Is it in the set? No, but it could be in the set. And so you use this if you have a really expensive operation. If this operation takes like seconds of time, but you could have a Bloom filter that says like a megabyte of 1s and 0s, and you can just flip a bunch of modulos in there, and to do the hashing function takes like 1 millisecond. Of course, you're going to want to do this because you may only have to do this every now and then, and you just only want to do it if it could be in the set. If it's not in the set, just don't even do it. And so Bloom filters allow for super fast maybes, and maybes are just way, way important.